It's my pleasure to give a very brief introduction for Professor Peter Grindrod from Oxford University to give the next plenary talk at MadeAI 2025. Professor Grindrod is a mathematician from Oxford University, has done many works in his long career. I'd dare to say he's an unusual mathematician, done so many different things. He was very high up in the UK research council system, being involved in several research councils, and even served as a director role for many years. The largest research council in the UK, the EPSRC, where Pete served as a director for some years. Beyond that, Peter is very active in innovation. He has set up, I lost the count, many companies, startups, and he's working on a new one recently on AI. This is the reason why he couldn't be here this time. I said I won't blame you. It's millions of pounds waiting there. So, and Peter was here last year for the first edition of MadeAI, and Peter has very interesting view from the foundation, the mathematical foundation of AI, which was very deep, the thinking, and everybody was impressed. And this is why I, at the venue, extended the invitation to Peter for plenary this year, and Peter kindly agreed. Peter is also a CBE. For you, those who come from Europe, you might know what it means. If not, let me explain. So that's Commander for British Emperor. So in the UK system, for good citizens, or established citizens, maybe I put it that way, you become recognized by the king or the queen, and you have a special title attached to you. And CBE is probably the second highest one, if I'm right, in that system. So very few people receive that. It's not just for academics, it's for everybody. I think the last year, was it the famous British tennis player Andy Murray received for his long career contribution. So it's not really easy to get there. But here we go. Pete is one of them. So for his contribution to research and development in mathematics. So with all of that, I'll shut up. Pete, the floor is yours. Thank you.
Okay, well, thanks very much, everybody. Thank you to all my friends on the organising committee for inviting me along. And I'm particularly fond of the concept for these conferences, because I genuinely believe that you can't innovate without having some idea of potential applications and some idea of the problems and pains of the current technology, so that you can invent new things and new ways of approaching problems that enable you to do things that genuinely can't be done today. And so all of us here at this conference, we're fortunate in that we have the experience of making applications, of trying to innovate with successful AI, successful data science. But that puts us very close, very up close, and it's very personal when you see what's difficult, what's easy, what's impossible with the current. And today I want to have a bit of fun, because I'm going to talk not about things that we all can do successfully. I want to talk about things that we might be able to do in the future. And so it's a bit of fun, really. I don't want to spend time talking about successful applications of things. I want to talk about things we cannot currently do, which maybe one day we'll all be able to do. And I believe strongly that it takes people like us, and particularly early career people, not just old people like me, but early career people who can push these things forwards. It's fundamentally a creative act, and it's something that will bring us hopefully a lot of success, and hopefully a lot of joy at the same time. Okay, so I'm going to talk about really next generation AI. And in military terms, in the military, we tend to talk about next generation stuff, and then we talk about generation after next stuff. And I suppose a lot of what I'm talking about is generation after next, but some bits of it are next generation. And I've just started a company called Astute, without any astut.co.uk. I've started a company called Astute, and we're going to do some of these things, but only some of them. Most of the stuff I'm going to be talking about today is presently not possible, but clearly there is a path from where we are now to where we want to be. So the topic is neuromorphic information processing and neuromorphic AI. And simply, neuromorphic means that we're taking our inspiration from the way in which the human brain is doing things, and we're trying to emulate things that the human brain can do. Well, that is artificial intelligence, isn't it? It's emulation because it doesn't really do simulation. It doesn't do it in the same way that the human brain does it. It just does things which are apparently similar to the things that the human brains can do, but it's emulation. But if we think about simulation, if we think about processing information and doing intelligent things in the way that the human brain actually does them, or apparently actually does them, then we get all sorts of new ideas for AI, the fundamental technology, the concepts, the methods, and most importantly, the valuable applications. And you know, competition is a big driver in science. It's great to be first at something, and it's great to be the best at something. And I think for early career scientists especially, you know, you should aspire to be the first to do things and the best to do things. Those aren't necessarily the same, are they? Okay, so we're going to talk about neuromorphic computing and neuromorphic AI. And I'm going to do this from two perspectives. So the first perspective is to have a think about how the human brain actually works and what can it tell us about how future chips, instead of doing what the current chips do, how the future chips might do things differently and enable a different sort of information processing. And then I'll talk about things that, this is my favourite topic, things that the human brain can do which present AI doesn't seem to be able to do. And there lies a need for neuromorphic information processing, but also a challenge and a goal and a big prize for all of us to be able to extend science and extend artificial intelligence into this next generation. And then at the end, I'm happy to take any questions or criticism or observation that you guys have. So when we look inside a human brain, what do we see? Well, we know what we see. We see about you've got about 1.5 kilograms of wetware, and the human cortex is corrugated over the top of your brains, and it contains about 10 billion neurons. 10 billion neurons, that's still a big number in my family. 10 billion neurons. And that means that directly simulating 10 billion dynamical processes all linked up in some network would still be hard work. But just by thinking about it, we can learn stuff. And I'm going to tell you about some of those things in a moment. So with this 10 billion network of neurons, the neurons connections are directed. So neuron A might be connected to neuron B. So if he fires, then it travels, and then he hears it and he might fire. But that doesn't mean that neuron B is connected back to neuron A. It possibly is, but it might not be. So, you know, we're looking at very, very large networks, but they're not random networks. The neurons are coupled up in a kind of network of networks. So the inner networks each contain about 10,000 neurons, so that's 10 to the 4 neurons, and they're very densely connected. And then you've got about 1 million of those. So they're in a two-dimensional array, roughly 1,000 by 1,000. So if you imagine taking your cortex off your brain and flattening it out and ironing it out like you iron your shirts, get rid of all the corrugations, you'd have about 1 meter squared of cortex, and it'd be like a carpet. And each of the carpet piles, each of the tufts of carpet, is what's called a neural column. And those neural columns each contain 10,000 neurons. So we've got 1 million columns, and each carpet pile contains 10,000 neurons. So, this is big to try and simulate. And we have tried to simulate some of these things with supercomputers. We have a computer in Manchester called Spinnaker, which has 1,000 cores. So I'm speaking to you with my Macintosh, that's dual core. It's got 2 cores in it. When I want to simulate a human brain, I have to go and find a computer with 1 million cores in it. And those are so specialised, those computers, that it takes a year to learn their own operating system and to be able to code up on them and things like that. It's not a straightforward process at all. But just hold the concept. We don't need to do it today. So just hold the concept. So there are these sort of neural columns, each of which contains 10,000 neurons, and the columns themselves are loosely connected up. So it's an outer network, which is sparse, of inner networks, which are dense. And in mathematics, we've got a name for that. We call the inner networks modules, and we refer to the whole system as having a high modularity, meaning that it can be decomposed into lots, in this case 1 million, of much smaller dense modules. And there's a whole business started off by Mark Newman, very famous mathematician and physicist, to take any old network and try and decompose it into modules. But in this case, I'm not interested in any old network. I'm interested in the network of the human cortex, and anatomically, it's split into modules. And we might ask, well, why is it split into modules? Why isn't it just a more random network? Or why aren't the modules all of different sizes? And I'm going to explain that in a moment. When we have a look at what an individual module can do, it's got 10,000 neurons. We can simulate it. We can take 10,000 active neurons. The neurons are excitable and refractory, which means that if they're stimulated, they'll suddenly spike, and then when they've spiked, they need a little refractory period while the ions either side of the membranes recover, and it gets back to be ready to spike again. So it can't spike immediately it's spiked. It has to have a little rest period. It's called the refractory period. And then it's ready in excitable mode again and sitting there quietly waiting to be spiked. Just like our students when we're lecturing them, they're sitting all quietly waiting to be stimulated with good ideas. So the neurons are the same. When you find out what happens with a set of 10,000 densely connected neurons, it's kind of quite interesting what happens. They behave a bit like multi-dimensional clocks. That's a clock. A normal clock has a single phase, which goes round and round and round. But a multi-dimensional clock has multiple phases, and they're all going round at different rates. And you could think of that as a dynamical system on a state space, which is a high-dimensional torus, typically 10 or 20 dimensions or something like that. So we could model individual neurons as sort of 20-dimensional clocks. A 20-dimensional clock is just a one-dimensional clock cross a one-dimensional clock cross a one-dimensional clock. You're taking Cartesian products and you're forming high-dimensional tori from S1, which is just the circle, or T is the same as T1. So T20 is just 20 copies of T1, which is 20 copies of S1. Why is this important? Well, it turns out that it takes a bit of time for the message from, say, one neuron to be emitted, go out along the axon, jump across the synapse in the longer dendrite and arrive at the next neuron, and then that one fires. And then he fires, so a signal is emitted, goes out along the axon, jumps across the synapse, comes up along the dendrite, and then the next one fires. This takes a bit of time. And in most chips that have been designed by companies like Intel, the Low-Hi chip, and IBM, the True North chip, those times are set to be discrete times. In fact, they're integers, and they're usually equal to one time step. So you could think of all the times that's been rescaled so that they're equal to t is 1. It takes 1 second for this guy to stimulate this guy, and another 1 second to stimulate that guy, and so on down our chain. When you do that, and you do that experiment, you realise that you lose the vast amount of behaviour that's possible. If you just remove the constraint that this is in discrete time and that the time is just updated at integer times, if you remove that and allow real-time delays, so it could be random numbers, suitably distributed, choose your distribution, don't care what it is, but there's some variableness, or a trembly hand, then you find that these individual columns can show a huge amount of different types of dynamics, because they're attractors for dynamics, which are devised on a state system, which is a high-dimensional torus. And when you look at the design of neuromorphic chips, they almost all, for pragmatic reasons, make the assumption that time just updates at the tick of a clock. And they all do it, because then it's easy. They just know what the state is, and they update the state, and they update the state, and they update the state, and they update the state. And in doing that, they've thrown away about 95% of the possible dynamics for these dynamical systems. And you can do that experiment really simply on a simple Macintosh computer. No need for a fancy computer. It's only got 10,000 neurons. You can simulate the thing directly. Our brains don't do that. The pathways between the neurons, even within a single neural column, are tortuous, and they've each got an individual transit time. And when you simulate the same system and you generate real-valued transit times, you see immediately that you get a lot of dynamical modes that are possible, and you can measure this from the dimension of the resultant free-running attractor. The dimension of that attractor is roughly proportional to the logarithm of the size of the neural column. Let's think about that for a minute. If I take the size of a neural column, it's got 10,000 neurons, then the log of 10,000, log base 10, that's easy, that's 4. The number of dynamical degrees of freedom is proportional to the log, and this goes back to a well-known conjecture to do with cycles in random networks. We don't need to go there today, but this isn't too much of a surprise for network scientists. But nevertheless, it's a useful thing to think about, because it says that if you doubled the size of a neural column, you wouldn't double the amount of dynamics available, because it only grows like log. Okay, so really, if you wanted to double the amount of dynamic you've got available, you might as well, and you've got the space, rather than have one neural column which is twice as big, you'd be better to have 2 neural columns of the same size. Simple log-based scaling. And thinking about it, neural columns need to be big enough to be interesting, but now there's a Goldilocks effect that says if they're too big, then that's inefficient. It's a waste of energy and it's a waste of volume. The two things we're shortest of here are volume. Our heads can't be too big. Even at University of Oxford, we can't have big heads. We have to have smallish heads in order that we can be born. And we're short of energy. We don't want to be using huge amounts of energy that modern computers are using. We want to be using a small amount of energy. So if you think that you're volume constrained and energy constrained, it would be sensible for evolution to have designed the human brain so that it was just a huge carpet of similar sized modules. And that's exactly what I told you that we have. We have this meter square carpet, and all the modules are about the same size. They've got 10,000 or so neurons in. Now, if evolution developed individuals a long, long time ago, my parents, who happened to have a whole distribution of different sized modules, in general, those brains would have been inefficient and they wouldn't have been successful as individuals. They probably wouldn't have eaten much. They wouldn't have got boyfriends and girlfriends. And we don't meet their progeny around us today. We're all the product of the evolution of this very matter. And so that's why we've all got brains with a similar architecture. And it's a simple mathematical reason as to why we don't open up somebody's brain and find we've got distributions of sizes. What's the implication for people designing neuromorphic chips? Well, the first implication is that they're making a mistake if they do everything in discrete time. That they need to do everything in real time, and they need to have transmission rates which are involving real numbers. And of course, mathematically, that's going to look something like a horrendous system of difference equations for dynamical systems. And there's lots of time lags, and they're all real numbers. And we can't just update on the tick of the clock like Intel is doing, like IBM's doing. You can't discretize time. And as soon as you do, you lose all the exotic behavior. What sort of exotic behavior are we interested in? Well, if you take the whole thing, if you take the whole network of networks and you spike it, that's equivalent to, say, the brain receiving some stimulus from your eye or from your ear or from some sensory stimulation, and it comes and it starts to stimulate this in some way. Then we can watch as the response to that simulated pattern spreads out across the cortex and moves to relevant parts of the cortex. And when we do those experiments, what we find is that the brain doesn't just respond in one way for one signal. It's not really one-to-one. For different signals, it responds in maybe very similar ways, but there are a very large number of dynamical modes which are possible. And these modes are the responses to incoming stimuli. And what I'm saying is that you don't really get an individual response to each individual stimuli. Actually, the whole dynamical system responds in a modal way and produces patterns in time and patterns across the whole network, which are sort of categorizing what is going on. And those patterns are actually very good candidates for things like internal phenomenological feelings, like anxiety, like envy, like embarrassment, like love, like fear, all of those sorts of things. They're a result of incoming stimuli, but they also precondition the system to receive the next stimulation. So here there's a useful idea that when we think about, just in this thought experiment, without doing anything, what the human brain is doing, actually, by having these dynamical modes which are present at one time, I've preconditioned the brain. So when I'm feeling anxious and then I hear a strange noise coming in, I'm immediately fearful because only bad things are going to happen. When I'm sitting next to my loved ones, only nice things are going to happen. And I hear the same noise and I go, oh, it's great, something good's happening. So actually what's happening here is that these internal dynamical modes are preconditioning the human brain. They exist very naturally. If you've got the neurons, if you've got the time delays, if you've got the architecture, your brain has these dynamical modes. And those dynamical modes, once they're there, then they precondition the processing of the next incoming signals. And that massively cuts down the work. It means that we don't have to constantly consider every possible thing is going on all of the time. We can actually make decisions from a reduced decision set. Only awful things are going to happen. I'm feeling anxious. Only terrible things are going to happen. Which of the terrible things is happening? That's a much easier decision problem than thinking anything possible could happen and I need to consider them all and compete them in some Bayesian way or some decision-making way or something like that. So actually there's an evolutionary, what's called a fast-thinking advantage to being able to do this. And of course, this was picked up quite a number of years with the attention mechanism, which was invented, where the attention mechanism, roughly speaking, says that machine learning model doesn't have to do everything all of the time, that it can focus attention onto the elements of signals that really matter, and it can have a very fast decision made by focusing attention. And this is, of course, at the basis of the architecture that is the basis for large language models now. And so we've seen something similar with attention, and I'm saying in the next generation we'll see it won't just be about attention, it will be about the mood or the mode that the computer processor is in. Just like your boss or just like your partner, the answer you get may depend on the mood they're in when you ask them the question. So we're going to have to get used to that we can massively cut down the amount of work required if we allow some preconditioning and for that to be modal. Now, this is we've already seen the success of the attention mechanism in AI and the autoencoder and the large language models and things like that. And what I'm saying is that this idea has got a whole way to go. And the human brain does this effortlessly. You've got thousands of different modes that you can be in. There isn't just attention on and off or particular attention focus on and off. You've got thousands of modes that you can be in. And actually they're arranged hierarchically. I haven't got time to explain all of that, but they're arranged hierarchically. And depending on which dynamical mode you're in, the mapping from new input to new output, from new stimulus to new consequences, will be slightly dependent upon the preconditioning that's provided by that mapping. And as the people like Daniel Kahneman and Eamon Tversky have shown, is that it's actually very difficult to stop a human brain from doing this. This is your fast thinking network. And it means that we can come up with the solution to problems very quickly. We don't have to solve the whole problem. And if you want to stop yourself from fast thinking, from using heuristics, which are known problems, which Dan Ariely calls predictably irrational, actually you really have to put in some concentrated effort in order to prevent your brain from doing that. So what we're going to see is much faster information processing by allowing for chips to work in real time. Effectively, the future of digital is analog then. It can't just be all updated on the tick of a clock at integer times. We've got to allow for real time. And then we'll get this benefit from having a huge number of dynamical modes, each of which we can learn to precondition incoming sensory stimulation in the form of problems which require some sort of reaction or some sort of decision making, something like that. So just by looking at these simulations, and actually we haven't looked at any today, just by thinking about them, we can see that, part of the next generation of AI is to admit some modal thinking, is to admit that we should be able to, on the hoof, precondition AI to get into different modes so that we don't have to boil the ocean for every possible decision. And that won't happen without a redesign of the chips to produce new forms of neuromorphic information processing. Now, I'm not talking about quantum processing, that's something else. That's not neuromorphic either. I mean, there's nothing in the human brain that's happening on quantum physics timescales or temperatures or levels, but it's just another form of non-binary processing. And what I'm talking to you about here is a very natural non-binary processing, and we all do it. We've all done it since we were babies, since before we were born. We've got this 1.5 kilograms of wetware, and it became sophisticated when we got to adolescence, and we had a lot more neurotransmitters, so a lot more learning, a lot more evolution of the network, until we've ended up with these networks, which are networks of networks, which are highly modular networks, and they admit this sort of neural thinking. So the first thing to take away is that there will be next generation chips, very likely, and we'll have to get used to them, because the outputs they give, the way they perform, will kind of depend on what's gone before. They're self-preconditioning, okay, which sounds a bit scary. It sounds like we've let go of the of the dynamical system. And, but that's kind of like the expert in the next room. When I pop in to see my boss and I ask him a question, can I go to Portugal this afternoon? Can I spend the money and fly to Portugal? Maybe he'll say yes, maybe he'll say no. And some of that depends on a rational decision, his algorithm, and some of that might depend on the mood that he's in. So, we're all used to managing this, but of course we're going to have to get used to managing this in forms of AI. Some of you will think, well, this is terrible because AI just became inconsistent and things like that. Others of you think, yeah, but now this allows AI to get to problems that we can't get close to at the moment because they're so complicated. It will allow AI to become much more approximate. It will allow AI to develop its own form of reasoning heuristics and that sort of thing. Let's move on and let's think about the brain from another angle. That's all I want to say about large-scale simulations. Oh yeah, I'll just say one more thing. Of course, there have been in the US and in the EU very large-scale brain simulation projects. And for all sorts of reasons, the Human Brain Project was one in the EU. And for all sorts of reasons, those projects failed. They cost a lot of money, and they were funded competitively to other things that might have been funded. But for all sorts of reasons, those projects largely failed because they got bogged down, not just in politics, but also in all sorts of other things. And I think it's a big disappointment that they failed. Where we can benefit now is that we can use those computers. I use one of those computers to do the things that we want to do and the sorts of things I just talked about. But largely, the ability to do full simulations of human brains and to demonstrate machine consciousness is still out there and hasn't really been successfully addressed at all. And indeed, those two large projects, one in the US and one in the EU, have largely just hunkered down and gone and done something else now. And they've sort of reined in their ambitions, which is a pity. But given the nature of multinational, multi-investigator projects, it was probably inevitable that there'd be some sort of disruption or some sort of disparity there. That doesn't mean we shouldn't learn from that and what went before. So brain simulation has taught us some simple things. It's taught us that scale matters, that you have to do things at large scale. You can't muck about with 100 neurons and call that a human. A neural column has 10,000 neurons, it's robust, but actually then it doesn't need to be any bigger, so then we can have lots of copies, and you've got about 1 million copies. Sadly, every time you have a drink of delicious Portuguese beer, you're probably killing a few neurons, but you've got plenty to play with, so we're all right for the time being. Okay, I want to move on and consider some things that the human brain does, which AI can't do, but it might do in the future. And one of those drives my new company, which is called Astute. And one of the things we're doing is we're working in the area of making decisions where you haven't got any data. Making decisions in situations that you've never ever experienced before. Now, my mum is very good at this. If you put her in a situation she's never experienced before, and you ask her a question, about it, shall we get into the car and drive away, she will give you an answer. She doesn't say, I got no idea, I've never experienced this before. She's always got an opinion, rightly or wrongly. Say that's a good thing or a bad thing. Okay, so I'm very interested in situations where we don't have specific data from which to calibrate a decision-making algorithm. But actually we don't know nothing. We do know something. We know what doesn't work. We know that gravity acts downwards. We've got policies that we wouldn't do things that would kill people. We've got legal requirements that we mustn't murder anybody. We've got all sorts of other things which sort of rule out decision options. They aren't enough to build a concrete case towards a particular decision option. But given an unusual decision to take, actually I do know things which could refute decision options. And so that's an area we're working in. But this is part of a larger scale problem. Let's think about a few things that human brains can do, which computers can't really do at the moment. So the first one is abstraction. A lot of people write about this, and it's very well known that when you talk about specific things like different types of say animals, of say horses, dogs, cats, they've all got 4 legs, they've all got a head, they've all got a tail, that's an animal. So when we're confronted by an animal like a lion that we've never seen before, we can see it's got 4 legs, it's got a head, it's got a tail, it looks like an animal. I'm able to abstract the concept of being an animal. Now there's good evidence to show that large language models can do this directly. Part of my research at the moment is in this area, where we're able to show that the encoding of words, being able to substitute one word for another word. So suppose we've got a load of words which are complementary words to say about British academics. He's good looking, he's handsome, he's clever, he's wise. These are all words that people would use to talk about people like us. They're in a class called words that we would use to compliment people on their fine abilities and that kind of thing. And if I start using a new word, if I just make a word up, but I use it with everybody in such a way that clearly I'm meaning to say something complimentary and it fits in where all those other words would have fit, all of your brains will intuit the fact that this must be some word that means something complimentary or something like that. And large language models can do that too. It's quite interesting that the clusters of words which have similar friends of friends, so they're related, they're sort of substitutable and things like that, those clusters of words actually, the cluster themselves represents the abstraction, and so that's there, it's in there. And there are lots of other ways that people try to use abstraction as a way of creating explainable AI now. AI that is more trustworthy and better justified and things like that. So abstraction, being able to abstract from the particular cases that we as scientists and engineers are considering, to consider whether or not we're encapsulating knowledge that could apply in slightly different areas and would intuitively map what it's capable of in the area which we built it for into some new areas. That's really what we want in terms of abstraction. So that's a key goal for us. Second key goal would be hypothesis generation. Can I generate hypotheses about things? If I say to a computer, why would I go to watch a soccer game today? Then it comes back with a list of answers. Say, because it's quite exciting to go and watch a soccer game. There's a big crowd and there'll be a lot of shouting, because there's a chance to see excellence on display, people with incredible skills, because there's some singing and passion amongst the supporters, and so there's a feeling of bonhomie and fun amongst the supporters. It might say, because it only takes 90 minutes plus 15 minutes, you'll be back home in 2.5 hours. That's quite a good use of time. It might give you all sorts of different reasons why hypothetically you might want to attend a football game. And this is now increasingly possible. And so one of the things that we're trying to do is to use something called novelty search, which is able to prime that sort of hypothesis generation so that we don't keep regenerating the same hypotheses over and over. So we prize the generation of novel hypotheses. We accept all the hypotheses we've already had, we've written them down, we've used them, we've thought about them. And what we want now is to see more and more new ideas and have a method of creating new ideas. So this isn't trivial, but the building blocks are there. We've got ontologies, we've got abstraction, we've got novelty search, so we're able to prize novelty rather than maximize objectives, and we're able to generate hypotheses using various forms of generative AI, whether in language programming, as in chatbots or something else. Okay, we know that all those pieces exist, but they've never really been put together in that way. So hypothesis generation is really the sort of beginnings of something, because it says, can we generate novel hypotheses? And actual fact, when I started to think about this, I want to apply it to strategic decision making. So I want to say, we're going to make a strategic decision today. that's going to change the way we all work together. We've never had to do this before. What would be the reasons for making one decision over another? So that's strategic decision making. But other researchers last year and this year have published work on using similar approaches of hypothesis generation to planning problems, where they seek to come up with new ideas in planning problems and resource allocation. And also, intriguingly, there's some work on hypothesis generation for research directions, for trying to define new research questions that we might, as scientists, go and address. So where do research questions come from? Probably they come to us in our sleep or something like that. But if they don't come to us in our sleep, where are we going to get them from? And actually, there is some work to use processes like this to generate new potential pathways for scientific research. And again, that's kind of hypothesis generation. Let's go one step further. It's kind of impossible for computers to be imaginative at the moment. This is beyond hypothesis generation. It's imaginative, it's imagination. To imagine things that don't exist, or that, if you say to a large language model, should I teach my dog to talk? The language model will go with you. It will say, oh yeah, teaching your dog to talk would be good, because the dog could tell you if you were a good owner. It would tell you when it was hungry. It would tell you when it wanted to go for a walk. Even better, it would be very valuable to have a talking dog, because you could put it onto TV and it would make a lot of money and would become a big TV star. Okay, the thing sort of goes with you, but you had to do the imaginative step of starting to think about something that doesn't exist, the talking dog, right? If you just sort of say, I'm a pet owner, how could I make some money? It won't suddenly say, well, you should teach your dog to talk, you're going to make $1 million. So getting computers to reliably go on imaginative voyages and to have an imagination. This is beyond hypothesis generation, right? And refutation of hypotheses. This is beyond. This is another step forward. One potential application for that would be in counterfactual reasoning. Now, I need to say that there are methods of checking AI which use counterfactual methods, but that's not what I'm talking about. They come up like SHAP analysis, and what they're doing is they're using a counterfactual argument to come up with performance measures that look at whether we've got the right attributes in an analysis or something like that. I'm not talking about that. I'm talking about the computer itself really doing what-if reasoning and producing counterfactual arguments. Say, well, if Pete was a murderer, he probably wouldn't have turned up to give a presentation this afternoon. He'd be on the run away from the police or something like that. There's a sort of counterfactual argument that you can use that says, well, if I had committed murder this morning, I probably wouldn't be here giving this talk. Although, interesting double bluff possibility there if I act normally. So counterfactual reasoning would be something that is both imaginative and extremely useful if we're able to do it. And at the moment, our computers can't do that sort of thing. So hypothesis generation, abstraction, refutation, being able to show that things that a computer has thought of as illogical and therefore can be contradicted. Counterfactual reasoning, show that the counterfactual implies something. Okay, that's next generation, or really generation after next AI. But those of us who are currently doing present generation AI, we should be thinking about those things, because shortly all the areas of big data, of rich data, will get mined out, and it's just a process of which branch of agentic systems or reinforcement learning or deep learning, and then how do we make it safe? How do we prevent it being spoofed? How do we prevent it drifting away from its calibration? All of those things are going to get sorted out. They're foundational things, and it's credible work for grown-ups. I'm not saying it isn't. Okay, but I'm saying when we've done all those things, actually the next generation and the generation after next is going to have to take us on to... So I just want to finish by saying, well, this would be we need a culture change as regards to our use of AI. You see, we've become used to having AIs that are consistent. So if I set up an AI to, look at computer vision and try to tell me whether what I'm seeing is a cat or a bird, then there are lots of different ways to do that, and the progress with computer vision is extraordinary. I can do that. Okay, and it does it consistently, and if it makes a mistake, it will make consistent mistakes, becomes predictably irrational. It's consistent. But if I get AI which is mood dependent or mode dependent, if I get AI that is using novelty search, then one instance of AI might have different blind spots than another instance of AI, just like people. So one instance of the AI might have a very thorough coverage of mathematics, and another instance of AI might be not very good at mathematics, but rather good at some branch of logic. And so, they might give inconsistent results if they're asked a question in the intersection between logical reasoning and mathematical reasoning. And we're going to have to get used to that, aren't we? It's a bit like dealing with people, that some people bring some baggage and other people bring different baggage. And if we ask them the same question, they might give slightly different answers. That's their truth. That's in their experience, in their subjective appreciation of what we're talking about. That's the result as far as they're concerned. So actually, one of the things that we're going to have to get used to is a culture where AI loses this ability to be an all authoritative algorithm, an all authoritative reasoning machine. And it becomes much more like a subjective opinion, like a reliable friend or a trusted expert that's giving us the best advice we can give it. But there still needs to be a human in the loop. And one of the things that I say to people who are worried about AI removing all the jobs and the grunt work and things like this from many industries in many different sectors, actually there's still going to be a need for people to decide, because as the AI gets smarter, it's going to become more subjective, it's going to become more individual, and it's going to have less collected consistency and authority, and it's going to be more like a present opinion, given the evidence, given my experience. It's a subjective expert opinion, and that's the way this is going. Okay, so we've done quite a bit. I've just talked to you about the need for next generation information processing and how that needs to differ from this discrete time updating on integers. We need to get away from that. And then we'll develop non-binary chips, which are really concoctions of multi-phase clocks all linked together, phase resetting each other, things like that. Necessarily that has modes, which are like moods. Necessarily that will be a huge extension to what we already know is successful, the attention mechanism that's used in modern AI for the last 10 years or so, which has been extraordinary. And that's going to happen, but in much greater ways than it ever has before. I'm saying there are challenges out there for us to think about. And remember, we're the best people to think about it, because we're aware of the pleasures and pains from the successes and the shortcomings of current AI. So we can define use cases that would be useful in developing the new AI. All of this could result in a fresh start for cognition and consciousness studies, with a much more mathematical framework that would allow for the directed development of new algorithms and of new information processing chips, which move us from where we are now into the direction of where the human brain is. Now, to do that, we need a common framework which is big enough and flexible enough to include all of the current concepts, including the performance of human brains, and have it all in one circus, have it all in one collection, so that we can see where we are now in terms of emulation, where we are now in terms of algorithms, and where we want to be when we want to be able to perform as a human brain does. Even in some of these I haven't talked about consciousness and anything like that, or conscious experience of things. I've talked about refutation. I've talked about hypothesis generation, talked about abstraction, I've talked about counterfactual reasoning. These are all super exciting areas for us all to work in. I'm going to finish there, but thank you very much for listening, and please, any comments and questions I'd really like to hear.
Thank you very much, Peter, for giving the very inspiring, stimulating presentation. So we have about 10 minutes to take questions. Any question? First one?
Can you hear me from here?
Yes, I can.
Yeah, okay. So with large language models, we train them to be as factual as we can, because that's our point of reference. However, when they hallucinate, sometimes they have some of these characteristics, some sort of creativity. It's a bit childlike. So the younger they are, the more visible is that they are making it up. Yes. So I feel that maybe in the language it is encoded already, this information, this type of ability. We're just sorting it out with our methods of training. Have you tried to just use it?
This is a great question. So let me come back to that in a moment. I just want to capture something you said there, which I really like. That's a bit childlike. And what we're seeing is when they start to go off at a tangent or hallucinate or things like that, or produce things which are just fallacious or fantastic in a real sense, they're very definitely a bit childlike. And of course, why wouldn't they be? Because there's no sort of really feedback or reward or reward system or punishment system for being that way, and we haven't really thought about them in that way. So, but let's turn the negative into a positive. I think that, as I said, when you look, if you can look at the way these say raggable large language models are created, and you can find that if you embed all the words that they can use into some super high dimensional embedding space, might be thousands of dimensions, you can find that there are clusters of words and things like that, and no doubt these clusters do represent more abstracted meanings, and they allow the construction of plausible sentences, which may or may not be fantastical, which may or may be realistic or maybe childlike and naive. I mean, there's nothing there. There's no break on that. But I think this is actually quite encouraging, because it shows that in the process of almost like creating the building blocks of building words on words on words on words on words, which is kind of what babies do when they acquire language. When they try and get to more sophisticated problems, they're able to access something else that's been sort of grandfathered in, and that is this sort of ability to have some abstract attributes and attributional meanings. And you'll know there's quite a lot of work in this area. My son is a philosopher, and we've been doing some work together. He does the philosophy of language. We've been doing some work together. I've been doing some of that with him, and we'll put something out next year. But it kind of shows how the non-uniformity of the word embeddings, so the clustering and things like that of the word embeddings, the non-uniform density of the word embeddings, actually is very, very useful in terms of inferring different types of meaning, like iconicity, concreteness, rude words, the sophistication of words, which you could measure by the age at which they're acquired by human beings and things like that. So there's an awful lot of attributes we can apply to words, these psychological attributes, and yeah, all of that stuff gets grandfathered in there. So I'm not surprised that, maybe to us at first it seems childlike and sort of obviously fallacious, but this is like a child learning to start to reason. What we need to do is to not preclude that. We need to find some way to harness that and make it better and make it more reliable, so that we can develop the AI as an expert. as an expert, would have fantastic bandwidth, would have fantastic capacity. Can we control it so that it doesn't, become dangerous and delusional, like some academics do, become dangerous and delusional? I think, do you see that challenge in your work? Is that something you're doing?
No, it's not very related, but when I use the AI sometimes, yes, I feel that there is the current technology, the current way we're doing stuff, so without necessarily doing this hardware transition, this discrete versus continuous changes, which are very, very, very difficult, as you say, but that very likely there's something to be exploited already. Maybe we cannot do it reliably, but maybe we can. So that's what I wanted to know, that is there work being done in that direction?
Yeah, well, for sure. I mean, I went to China recently, I was talking about their large language model in China, and of course, we've gone from sort of nowhere to where we are now in the last decade. I don't think there's a company in the UK or in Portugal that doesn't seek to use large language models in some way, shape or forms, maybe removing some report writing or doing some CRM and customer interaction or grunt work or something like that. Actually, unless we get hold of this, we've sort of developed a common point of failure. Because if those large language models were suddenly discovered to be unreliable and fallacious, I'm not saying they will, but if they were, then all these companies would have to change. I think also there's another challenge that we as scientists ought to see. So there's the common point of failure problem. There's another challenge that we all ought to see, and that is that the way in which we use large language models now might change very quickly. We've come a long way in a decade, and we might find that we can go, 100 times further in just one other decade. And so we should expect there to be, big changes in these areas. I think it's important that we're aware of the potential for common failures, and that we won't be able to do everything with these technologies. And so I kind of like it when people write papers not about how good the technology is, but how it fails. And I really like it when experts give talks about things we cannot currently do. That's what I've tried to do today, and talk about things that AI can't currently do, because I think that is inspiring to the next generation of scientists. But this is only going to accelerate. And we need to get hold of this in many different ways. But there's a big prize, both in terms of intellectually being able to understand and provoke and control and to manage, but also in terms of the value this brings to society in many different ways. And we should be extremely positive about it. Of course, the university sector tends to be users of AI, but we tend to be very conservative and not take enough risk on in terms of the types of things we're doing. So one of the reasons I've started a new company to do this sort of thing is it would be impossible to do the sorts of research I want to do within a university. The reason being that it's controversial, right? So if I tell 10 experts like you guys, 100 experts in a room that I'm going to do this, some of you will think, oh, well, this is great. Others of you will think, this is terrible. The guy's crazy. Why is he trying to do this? And it starts a fight. And it's not possible to fund that sort of controversial research through peer group review, because sooner or later one of the referees isn't going to like it and it isn't going to get funded. But nevertheless, if you're really committed to it, and you want to do that sort of research, you have to find a different environment. And I'm saying that, for me, that involves leaving university and going back into a company. I've worked in companies before, so it's not a huge step for me. But for some people where you've had your career in universities, it's very difficult to somehow suddenly switch and go out into a large corporates or even small startups. It's a big cultural change, but I think it's necessary. And if you say, well, who is inventing AI today? Who owns AI? Then probably the best answer is Menlo Park in California. And you certainly wouldn't say the University of Oxford or the University of Cambridge owns AI, because we don't. We get blindsided by some of the fantastic development and some of the disruptions that come out of AI. And largely those are done in environments where risk-taking is normal, and we're not, just taking an average of 5 experts. So I believe strongly that we're not going to get this stuff done in the public sector in the UK. And I'm saying that sadly after almost 25 years of working with UK funding for science, for AI and applications. But I think, the public purse should be spending money on foundational things, but when it comes to high risk, fail fast things, it's very difficult to justify that with public taxpayers' money, and you have to go and get shareholders and use private money and use venture money to do that.
Thank you very much, Peter. I'm sure there will. I can see there are more questions, but I'm cautious about the time, so forgive me. Peter.
Well, if there are any other questions, collect them up, pop them in an email. You guys know how to find me, and I'll happily answer any questions online that you've got. Just send me an email and let me have it, good and bad. Comments as well as cheerful, challenging criticism, please. And thanks very much for your time, everybody. I really appreciate the opportunity to talk to you all today.
Thank you, Peter. With that, I will share your contact with the audience after the conference. I myself had some tough questions after your inspiring talk, but that will be involve probably half an hour questioning time. Thank you again, Peter.